In this video, we're going to look at how to calculate permutations. This is another type of thing for figuring out how many you can have in a situation for our counting theory that we've been working on. In a previous video, we looked at arrangements. And arrangements were the idea is if I have 10 things, how many different ways can I put them in order? So the example I'm known to use a lot is if I have 10 cars, how many ways can I park them in my 10-car garage? For permutations, it's going to be pretty much the same idea, except we're not going to arrange all the items. So it might be something more like I have 10 cars, how many ways can I choose 3 of them and then park them in my 3-car garage? Or if I have 10 friends, how many ways can I choose which one's my best friend, my second best friend, and my third best friend? Like that. So it's the same idea of putting things in order as arrangements are, except in this case we're not going to put them all in order. We're just going to put a select few of them. I do want to say here up front that this delineation between permutations and arrangements is something I do to just give us some more handles for sorting out counting theory. Oftentimes these are not delineated. They're all treated as permutations. So oftentimes in different texts you'll hear permutations where sometimes you permute all the things, sometimes you only permute a handful of the things. So it definitely has that flexibility, and so what I call arrangements are actually permutations. I'm just making that distinction for the sake of unpacking all of the different concepts in a step-by-step approach so that it's not so overwhelming for students who are learning it. So let's look at that example I just talked about where we have 10 cars and we want to figure out how many ways I can park 3 of them in my 3-car garage. So this is, again, something that I want to tie back to our fundamental counting principle. When I talk about the fundamental counting principle, I basically emphasize that we have slots that we're trying to fill, and we need to figure out how many ways we can fill each of those slots. Now, in this case, our slots are literal slots because they're the garage bays. And so we have our first garage bay, we have our second garage bay, and we have our third garage bay. Now, in terms of our cars, we have 10 choices for which car we park in our first garage bay. And then we have 9 choices for which one goes in our second garage bay because we've already parked one, so we can't park it in 2 different slots. And then we have 8 choices for which one goes in our third garage bay. Then our fundamental counting principle tells us to figure out our total, we have to multiply all of these up. And then that's going to give us 720 different ways we can park those. So really with these permutations, it's just a specialized application of the fundamental counting principle. That being said, I want to present this in a slightly different way. I'm going to leave what I have on the screen. But there's a slightly different way we sometimes think about this. So if you think about when we talked about arrangements and our 10 cars in our 10-car garage, we parked all of them, and so it was 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And because we don't like to say all that or write all that out, mathematicians developed this idea of 10 factorial. And so what I want to do here is kind of work this exact same thing out. We're not going to get a different result than what we've already gotten, but work it out using this factorial notation because it's just sometimes more handy. When you're dealing with 3 things, it's not that big of a deal. But what if we had 63 cows and we were trying to select 34 of them to go to the other pasture? Well, now if we do it like I did just above, then we have a lot more writing to do. But let's do it using this factorial notation. So let's say we have our 10 cars and we want to park them in our 3-car garage. Well, this is kind of a counterintuitive way of thinking through it, but basically I can range all my cars from the one that I want to choose first down to the last one, and that would give me 10 factorial. But if I'm choosing 3 of them, that means that there are going to be 7 of them that I'm not going to choose, and so that would be 7 factorial ways that I can arrange the things that I'm not going to park, or the cars that I'm not going to park in my garage. Let me write this out the long way so you can see what's happening. So when you get it all expanded out like that, what it becomes a lot easier to see is everything below 7 will cancel off, because anything divided by itself divides down to a 1. And so those are just going to get absorbed into the multiplication, leaving us with the 10 times the 9 times the 8, which is what we had up above. So I'm just showing you this because, 1, this is how it is most commonly expressed, and 2, to kind of help you wrap your brain around the 2 different ways of expressing something that amount to the same thing. I think the first one is the more intuitive way, but the second one is the way that we tend to lean on sometimes in mathematics when we get into much larger numbers, because they are easier to calculate out using the factorial function that is on most calculators. So let's go ahead and switch to another example just to make sure you're seeing how it works. There are 48 people in Faculty Senate. How many options are there for selecting a president, a vice president, and a secretary? So in this case, again, I like to process it using the fundamental accounting principle when there's only a few slots like this. And so we have our president slot, our vice president slot, and our secretary slot. I'm going to abbreviate that SEC. Okay. And then we could choose, of the 48 people, we can choose one of them to be president. We could also choose the secretary first. The math works out the same way. So there are 48 choices for the person who's going to be president. Once that person is locked into place, the same person can't be vice president. So that leaves us with 47 choices for vice president, and similarly 46 choices for secretary. Fundamental accounting principle tells us to multiply those puppy dogs up and get the total. All right, my handy dandy calculator told me that's 103,776. There we go. That's a lot. I'm glad I didn't have to list all those out literally to figure out how many there would be. I don't have time for that. So this example also gives me an opportunity to talk to you guys about something that is sometimes confusing to students, and that's this idea of naming the slots. These slots, president, vice president, secretary, or like we saw with our garage. It was the first garage door, the second garage door, the third garage door. Sometimes with passwords, it seems weird or confusing, like what would you name the slots? Well, it would just be the first character of the password, the second character of the password, the third character of the password. But this idea of naming the slots, one, it's going to be helpful for where we're going to next with our counting theory, is to be able to name the slots. But also I feel like if you can name the slots, then it's really easy to figure out, well, I shouldn't say really easy, but if you name the slots, it makes it somewhat easier to give you handles to figure out what numbers go in the slots. We are moving into a place where whether or not what the names on the slots are will affect what kind of choices we make. So for example, if you're doing lottery, like the Powerball, the first 5 slots would all be labeled white balls, and then I think the Powerball's like a red ball, and so you would label that 6th slot something different as the Powerball, and what you're choosing to fill the first 5 slots would be a different pot that you're choosing from than you are to choose that last slot. So I just wanted to take a second here at the end of the video to emphasize this idea of naming the slots. If you're struggling on a problem, try to draw out the slots and name them, and then ask yourself, when I'm doing this, like for president, vice president, secretary, am I selecting those three things all from the same pot? Whereas if I'm getting dressed and I'm trying to figure out how many different outfit options I have, my pants come from a different pot of options than my shirts. Those aren't the same thing. I wouldn't select them out of the same drawer in my closet, so to speak. Well, I mean, they can be stored in the same drawer, but you know what I mean. Anyways, I'll come back around to that idea of naming the slots and how it helps you with your decision making as we continue to develop more different kinds of counting techniques. For now, go ahead and give some of these a try and see how you fare.